now we will discuss very briefly about the spherical coordinate system, because it will be useful later on for us. So, let us go to spherical coordinate system now. Okay. Unfortunately, for spherical coordinate systems, we do not have a two-dimensional analogy that we could use, similar to Cartesian and cylindrical coordinate system. We had a two-dimensional analogy in those cases, and then we built up from two-dimensional to three dimensions. Okay. Unfortunately, we will not be able to do that with a spherical coordinate system. So, let us jump straight ahead to the three-dimensional spherical coordinate system. So, this is the spherical coordinate system that I am going to talk about. So, assume that I have a sphere, okay, and for the sake of it, I also will define the x and y coordinate systems. That is, I will define the Cartesian coordinate systems here. Sorry, this is y and this is x and this is the z axis. Okay. The sphere has a certain radius, we will denote that radius by r. Okay. Now, I am looking at this particular point P on the sphere, okay, of this constant radius r. So, imagine that there is a sphere and then there is a constant radius r, and this will be given by 3 values or 3 coordinates, just as we described a point in 3-dimensional rectangular Cartesian coordinate system by 3 values x, y and z, 3 coordinates. Similarly, we will have to give 3 coordinates for defining the point in spherical coordinate system, okay, and these points are r, theta and phi. Okay. What are these r, theta and phi? R is the radius of the sphere. Okay. So, when you are looking at a particular point, you can say that there is a point here and this is a unit sphere. Assume that this is my hand is a unit sphere, and where on the surface of the sphere is my point P located will be given by the radial distance or the radius of the sphere from the origin. Okay. This origin is the same origin for both spherical as well as for the rectangular Cartesian coordinate system. For the rectangular Cartesian coordinate system, you can imagine that there is a y axis here, okay, and there is a z axis from the top and there is a x axis coming off from here. Okay. So, you can imagine that one. Now, I have defined where I am located on the spherical, on the sphere, on the surface of the sphere, but I still need to give two other points in order to pinpoint the point P, right. So, one point would actually be very interesting. I have the z axis over here, okay. This is a sphere. I am sorry I did not bring an orange or an apple to show you the sphere, but you can find an apple if it is available, or an orange better if it is available with you, and you can try this hand waving experiments on that. So, you have a sphere, you have the z axis which is pointing upwards, okay, and my point is located at somewhere over here. How do I define this point? Well, all I have to do is I can now consider a line, okay, drawn from the center of the origin cutting through the point P. Okay. I have the z axis and then there is a point that is cutting through the point P, okay, a line that is cutting through the point P, and I measure the angle between the two lines. Okay. So, this angle is what I denote by theta, and this angle is called as elevation angle. What are the limits on this elevation angle? Well, you can be located right on the z axis, so which means that the angle theta is 0. You could be on the xy plane where the angle is pi by 2. You could be located at the bottom like earth south pole. Okay. So, you could be located at the bottom and theta will be equal to pi. It does not make any difference whether I am at the elevation of this point P or the opposite, or a different point which is at the same angle theta. Okay. So, these both are given by the same value of theta. So, I have the angle made between the two lines, which is the z axis and the line that is passing through the point P, and I call this angle measured from the z axis as theta. Am I done? Unfortunately no, I still need to give one more coordinate, right. I need to give you the value of phi. Now, here is where it gets little different. You need to drop a line, okay, on the xy plane. You need to drop a perpendicular from the point P onto the xy plane and then join the origin to this line. Okay. So, when you draw and drop this one, you are going to draw a line from the origin to the point P prime, which is exactly perpendicularly above, or it is situated by dropping a perpendicular from the point P onto the xy plane. Okay. Now, here this point P prime I know how to specify, right. All I have to specify is to give the angle phi. Okay. So, I have to give the angle phi. Now, here is a question, okay. You imagine taking an orange, okay, locate a point in the upper hemisphere and then try to insert a needle or a compass through the point until you reach the halfway xy plane. Okay. You can get the xy plane by just cutting off the orange and then you insert the perpendicular or you drop the perpendicular from the point such that it falls on the xy plane. Will that point have, at what distance will the point be from the origin? What is the radius of that distance? You can imagine drawing a circle around that, and then what is the radius of that circle? It turns out that this radius will be not equal to r, but it will be equal to r sin theta. Okay. Similarly, if you drop a perpendicular from p to the z axis, okay, so if you drop a perpendicular from p to the z axis, what you would find is that this length will be equal to r cos theta. Okay. So, this length will be equal to r cos theta. In fact, this is all giving you the conversion formulas, right. So, if this length is r sin theta, let us find the x and y components here by looking at x and projections onto the x and y axis. This length, you know, from the point p prime back onto the x axis has the value of r sin theta, which is the length of the radius or the radius, times cos phi, whereas the y value is given by r sin theta and sin phi. Okay. So, in fact, these are the conversion formulas that we were looking for. Okay. Z is r cos theta, y is equal to r sin theta sin phi, x is equal to r sin theta cos phi. Okay. Now comes the line integrals, the surface and the volume integrals. Okay. What is the line integral along the radial direction? The line integral or the line along the radial direction will be obtained by considering one sphere and you imagine another sphere which is whose radius is increasing from r to r plus dr. So, the difference if you move radially along will be equal to dr, okay, along r hat. Okay. Now, r hat is the radius vector directed in the radius on the sphere. Okay. So, along the radius of the sphere. Okay. What will be the line segment along phi? We know that in order to go to the line segment from point p prime, you will have to go to another point q prime. Okay. So, if you have a point p and a point q, you will now have to go from p prime to q prime. That would be movement of r sin theta along an arc length of d phi, right. So, that will be equal to r sin theta d phi along the phi axis. What will be the movement along theta? Well, you have a p here. Now, if you take one more point and then move, you have moved a distance of, or you have moved a angle of d phi, okay, from d theta. So, it is d theta as the angle that you have moved, but the arc length that you have moved will be equal to r d theta along the direction theta. Okay. What about the surface areas? The vector surface areas are ds along, let us say, r will be equal to, you need to move a certain direction along theta and a certain direction along phi, and these are the movements that you know how to move along. That becomes r along theta, r d theta along theta and r sin theta along d phi. So, we will give you r square sin theta d theta d phi and it will be directed along r hat. Okay. Similarly, ds theta, the surface element along the theta direction will be given by, you need to move along dr by a distance of dr and you need to move r sin theta along d phi. So, you get and dr along theta. What will be ds phi? Ds phi will be r d theta d phi along phi. Sorry, this is r d theta dr along phi. Finally, what is the volume element? Volume element is r square sin theta dr d theta d phi. Okay. This is the spherical coordinate system. The conversion formula from the unit vectors of x, y, z to the spherical unit vectors r, theta and phi, I am not going to derive that, and it is indeed little bit of a tediousness in deriving that one. You can look up the textbook if you want to get the answers. Okay. So, you can find out the conversion formula from the textbook and practice a couple of problems so that you know how to convert from rectangular to cylindrical, cylindrical to rectangular, cylindrical to spherical distribution. Okay. After taking this brief digression on the spherical coordinate system, we are now ready to discuss the point charge. The field of a point charge, okay, will be directed radially away from R. Okay. It will be directed radially away from R, and along a particular path, let me choose 2 points R2 and R1. Okay. I choose 2 points R2 and R1. I want to find out what is the potential difference between the 2 points. Okay. I want to find out what is the potential difference between the 2 points if I take this particular path. I am choosing this path because it is easy for me. The electric fields are radially directed away, and the path is also along the radial direction. Okay. So, the path itself is given by dlr is given by dr r hat. Okay. Do not include a minus dr over here. Okay. The minus dr will come on its own. Okay. So, this is dlr is equal to dr r hat, and then electric field is given by q by 4 pi epsilon 0 r square in the direction r. Okay. So, the potential difference V of r minus V of r2 is obtained by moving from point r2 to r1 E dot dl, right. Now, we are fortunate that E and dl we have chosen to be along the same direction parallelly. So, r dot r will be equal to 1, and then this integral becomes minus r2 to r1, and there is dr here. So, you have q by 4 pi epsilon 0 r square, and this is dr. Okay. Q by 4 pi epsilon is a constant, so I can pull this out. Q by 4 pi epsilon is a constant. I have integral of minus 1 by r square dr from r2 to r1. Okay. The integral of minus 1 by r square is, or the integral of 1 by r square is minus 1 by r, right. So, therefore, you can, and there is a minus sign here. So, this integral will become 1 by r. So, the potential difference that you are going to get V of r1 minus V of r2 is given by q by 4 pi epsilon 0 1 by r between r1 and r2, which will be q by 4 pi epsilon 0 1 by r1 minus 1 by r2. This is in volts. Okay. So, the potential difference is in volts. Well, this is a fairly interesting expression, because I can imagine going back or coming from R2 is equal to infinity. Imagine that I want to find out the potential at a point R1, but not from moving the test charge from R2 to R1 where R2 is close to R1. R2 I am going to push it away as far as infinity, and I will come from infinity to point R1 in the same direction of the radial thing that we have taken. Okay. So, I will come back from infinity to point R1, and I will try to find out what is the potential at infinity, as, or in other words, as R2 tends to be R2 becomes very large, 1 by R2 will be equal to 0. So, the potential at any point R, which is R measured from the origin, is given by q by 4 pi epsilon 0 into r, okay, where R2 is equal to infinity is taken as reference. Okay. You can see what is that. If I take V of infinity, R is equal to infinity, this expression will give me q by 4 pi epsilon 0 infinity. Okay. This will be equal to 0 volts. So, in other words, what I have done is to set R2 is equal to infinity as a reference for me to measure voltages. It is like sea level and the mountain, except that the sea level has been pushed away to the edge of the universe, to the end of the point infinity, so that all the other potentials at any other point in the space can now be called as absolute potentials. Okay. And it is interesting to note that the potential goes as 1 by r. Okay. You can kind of start suspecting some relationship between V and E, although we have already obtained that relationship here. You can try to think of the inverse kind of a relationship. Okay. V was obtained as integral of the electric field. Okay. So, you would suspect that electric field will be differential of voltage, and we will get to that one. Okay. So, we have set R2 is equal to infinity as our reference point. Okay. So, we have set R2 is equal to infinity as our reference point. Let us now consider some other types of charge distribution and electric field distribution and try to find out what will be the potential because of those charge distributions and line distributions. Before that, let us do a simple example. Okay. So, let us do a simple example. Assume that I have a point charge which is 222 picocoulombs. Okay. So, I have a charge which is 222 picocoulombs and I want to consider movement from R2 which is equal to 400 millimeters to R1 which is at 100 millimeters, and the field that we are considering is a point charge field. Okay. So, I want to find out what is the potential difference at 100 or potential difference between 100 millimeter and 400 millimeter points, okay, or the radius at 100 and 400, and I also want to find out what is V of 100 itself and what is V of 400 itself. Now, you can do it in two ways. One, you can write down that integral V from and integrate from 400 to 100. Okay. So, you can do this one. You have 222 picocoulombs divided by 4 pi epsilon 0 r square. So, let me remove the coulombs from here. So, you have 222 picocoulombs which is 10 to the power minus 12, and then integrating along, so moving along R2 to R1 from 400 mm to 100 mm. Okay. So, this is 100 mm. Okay. And the potential difference you can find out, you can integrate this expression and use the, or you can use the expression that we just derived, and you will see that this will be equal to 20 minus 5 which is equal to 15 volts. Okay. So, as you move from point R2 which is at 400 millimeters from the point charge to the point 100 millimeter from the point charge. Okay. So, you will actually experience a total potential rise of 15 volt. Okay. So, there is a potential rise if you move against the field. If you move against the electric field, you are going to see a potential rise. Okay. So, there is a potential rise of about 15 volts. You can of course from this expression itself find out that the potential at 100 is 20 and the potential at 400 is 5 volt. Okay. So, this is the potential at 400 mm, this is the potential at 100 mm. Okay. In fact, if you sketch the potential, okay, you do couple of other calculations like find out what is the potential at 100, 200, 300, 400 and so on. At 400 we already know what is the answer, 400 is 5 volt, and at 100 we know what is the answer, at 100 we have 20 volt. Okay. If you were to find out what is the potential at 200 millimeter from the origin, you are going to find out that this will be about 10 volt. Okay. And the potential is actually going as 1 by R. Okay. So, the potential is going as 1 by R. What will be the average slope if you take the 2 points as 200 mm and 100 mm? What will be the slope of this curve here? The slope of the curve will be 10 minus 20. The absolute value of the slope will be 10 minus 20 divided by 200 minus 100 mm. 10 to the power 3, let us put on top. This will be equal to 10 by 100 into 1000. So, this is 100 volt per meter. If you try to find out what is the potential, what is the slope of the potential curve from point 400 to point at 100 mm, the slope of this curve will be different compared to the slope of this curve. So, this simply indicates that if you want to find the slope and make it a good approximation to the continuous curve, your intervals be better small. Okay. So, the slope of this curve will be, so if we call this as 1 and this we call as 2, the slope of the curve 2 will be a total change of 15 volt, and the change in terms of this one is 400 minus 100. So, this is into 10 to into 1000, this is 300. So, you get 15 by 300, this is 1, this is 2. So, you get 1000 here. So, this will be about 200 volt per meter. The important point is that you can actually find the potential at different points. This is the potential at different points as a function of radial distance from the point. Okay. Indeed, what I wanted to highlight was you can actually find out the electric field, okay, at any point by looking at the slope of the potential curve. Okay. So, if I want to find the potential or the magnitude of the potential at any point r, I can find out what is the slope of the potential curve or the potential at that particular point. Okay. Of course, this gets better and better if I take the limit of delta r going to 0. So, in that case I get the electric field magnitude to be dV by dr. Okay. Thus, if I find out the maximum slope, okay, that will be the value of the electric field, and against the direction of the maximum value of the slope will be the direction of the electric field. Okay. So, we have seen this already, and we have also seen this in this particular charge distribution. I made a small mistake, my student corrected here. This is not 200 volt per meter, this is 50 volt per meter. Yeah, it was obvious, I did not see the division properly. Okay. So, this numerical value is 50 volt per meter. Okay. But coming back to the point that I was mentioning, the maximum value of the slope will be the value of the electric field at a given point, and the direction of the electric field at that point will be exactly opposite to the change of the slope. That is, let us say these are the constant potential surfaces, or what we call as potential contours. Okay. Constant potential surfaces or constant potential contours that I have measured on a piece of plane by some measurement methods which we will not have to go in here. So, we have constant potential contours here which are measured. Let us say this is 103 volts, this is 102, this is 101, and this is 100 volts. Okay. I want to find out the electric field at this particular point. How do I find the electric field at this point? I need to find where the slope would change, in which direction should I hunt. So, I actually try to find the slope along this one, I try to find the slope along this direction. Okay. I will also try to find the slope along this particular direction. Along line which is going backwards here, let us call this as line 1, line 2 and line 3. Along line 1 there is no change in the slope because the potential is essentially constant in that line, right. So, the electric field magnitude will not be affected over here, the electric field magnitude will actually be perpendicular to that. Remember, when the force is perpendicular to the object does not move. Similarly, when the electric field and the line segments are in the are perpendicular to each other, then the electric field, then the work done will be equal to 0 or the potential will be constant. Okay. So, along line 1 there is no potential change, along line 3 there is some potential change, as you go around there will be some potential change which you can decompose into potential change along say x axis and potential change along y axis. But very interestingly, the slope will actually be maximum as you go along the line 2, right. So, if you take a short distance between these two lines, the potential has changed by 1 volt. So, the electric field will be directed along this line 2. Okay. So, the electric field will be directed along line 2 with a value of 1 volt per meter. Okay. It will be 1 volt per meter, and actually the potential will be changing if you go in the opposite direction, right. So, if you look at the potential on the same line here, you will see that the potential change here is 1 volt per meter, the potential change here is 1 volt per meter. The direction of the electric field will be negative of the maximum slope. Okay. So, if this is the maximum slope, okay, and then the electric field will have to be directed in this way, because as you go against the electric field the potential must rise, right. So, if you go against the potential field, the potential must rise. Okay. So, keep in mind these 2 points. Okay. Electric field value will actually be equal to the maximum value of the slope dV by whatever direction, dV by dl for example, and the direction of the electric field will be against or minus of the slope dV by dl. Okay. So, if you remember this, and also remember that when you go against the electric field you are going to see a potential rise, then you can actually write down the electric field and potential contours. Okay. So, we are going to do that one. Consider uniform electric field. So, I have electric field lines which are going horizontal to the right, and these are all uniform electric field. Okay. What will happen to the potentials if you go opposite to the electric field from say some point which I have marked as here x to the point which I have marked as 0, the potential will be some value. Okay. We are not bothered with what the potential value is. If you take any parallel line to this same direction, the potential here will be exactly the same, because we are assuming that the electric field here is uniform. Okay. So, in fact, the potential will be constant along all this, on all the points along this line. Okay. These lines are called as equipotential lines. Okay. These are called as equipotential lines or constant, they are called as equipotential lines or they are called as constant potential contours, okay, or potential surfaces. Actually they would be surfaces in a plane way. So, if you take this one, there would be surfaces in a plane way with the electric fields all pointing uniformly like this. So, if this is the electric field, this is the surface that you are looking at. Okay. Now, suppose the electric field is diverging, it is not uniform in this plane, it is not uniform. Okay. What will happen to the surfaces of constant potential is that you are going to get the surfaces which are all going to, okay, my drawing may not be very accurate, but I am hoping that you are able to see a bulge in the surface here. Okay. So, as you go from a uniform to non-uniform field, the constant potentials will also be different. Moreover, a very interesting phenomenon happens. If the electric field is uniform, then the spacing between the equipotential lines is constant. So, let us say this is delta x and this will be the same delta x for the given potential difference. However, for the non-uniform electric field, the spacing between the equipotential planes, so if I assume that there is another plane over here, okay, this spacing delta x will be smaller than the spacing between these two. Okay. So, this will be smaller than this particular spacing delta x and delta x prime, for example. Okay. Because the field is actually getting weaker here, you need to move a larger distance to get to the same potential difference than you would have obtained if you had moved in a strong electric field. See, in a strong electric field you move a certain distance delta x, you get a certain potential. However, if you move in a weaker electric field, you have to the same distance, you will not get it. So, you have to move a larger distance in the weaker field in order to get the same potential difference, and that is how the potential contours or the potential surfaces would also start changing. Okay. They would also start spreading apart. Why are these field lines important? You will see sometime later that there are structures which are called as capacitors. Okay. And one of the very interesting aspect of the capacitor is to draw the field lines or is to compute the field lines. How do I compute the field lines of a capacitor? Assuming that the charge density is all uniform and the dimensions are very large, what a capacitor does is to induce charges of opposite polarity on its plates, correct. So, the charges are induced on opposite polarity of the plates, and the electric field lines begin from positive charge and terminate on the negative charge. As long as you are inside near center, okay, the field lines will all be uniform. However, if you start approaching the ends, okay, so as you start approaching the ends, you are going to see that electric field lines will start to bend and the separation between the two also starts to increase. This is something that you will find in a microstrip transmission line, for example. These fields which are at the edges are called as fringing fields, and calculation of fringing fields is one of the most complicated problems in capacitor calculations. Okay. So, in order to understand fringing fields, you need to understand how to draw the field lines, and in these cases the best method for obtaining the fringing field, or at least a very good approximation method for obtaining the fringing fields, is to go graphical, because analytically you cannot solve this problem easily. Okay. In fact, it is very difficult problem to solve analytically. However, by graphical methods such as drawing these field lines and spacing them apart so that the equipotential lines are properly matched, you can actually estimate the capacitance of a transmission for microstrip transmission line, okay, by taking the fringing fields into account. There are elaborate rules of how to obtain these fringing fields. We will not worry about those in this particular class for now. Okay. So, those rules are not, we are not going to worry about that. Okay. Before we move on to the next one, I want to consider the infinite line charge. Okay. So, we consider the infinite line charge and then try to see whether I can find the potential for this charge. Okay. So, I can actually find the potential for this charge. The charge has the line charge has a density of rho L coulomb per meter. At any given radius, we already know that the electric field lines are all radially outward and they are given by rho L by 2 pi epsilon 0 r r hat, this r hat is in the cylindrical coordinates. Imagine that there is a cylinder and then the electric field lines are all at any point r from the origin, the value is given by rho l by 2 pi epsilon 0 into r. Now, if I take a path very similar to what I did for the spherical charge, okay, if I take the same kind of a thing, I can actually try to find out what is the potential difference between 2 points. Let us say which is V of r1 minus V of r2, and I will be obtaining this one by going against the field from r2 to r1. I can substitute for the field here rho l by 2 pi epsilon 0 r. Okay. What should be the direction? Well, this is the same thing that we did in the last for the spherical charge distribution. Line segment will also be directed along r, and it is given by r, it is given by dr r hat. So, this line integral becomes a simple scalar integral. Okay. So, if you now try to find out what this is, you will see that the potential difference V of r1 minus V of r2 is actually given by rho l by 2 pi epsilon 0 ln the natural log of r1 by r2, with r1 being greater than r2. Oh sorry, I went from r2 to r1, right, sorry. So, this becomes r2 to r1, okay. r2 is the larger of the distance. So, I went from r2 to r1, and this will be the potential difference. Now, very quickly, can I use r1 is r2 is equal to infinity as my reference? Can I do that one? Unfortunately no. Why? Because if you try substituting r2 is equal to infinity in this expression, you will see that it becomes quickly ln of infinity, right. Of course, I can't use r2 is equal to 0 as my reference, because in that case also I will not be getting physically correct answers. Okay. So, what it seems to indicate is that for an infinite line charge, I cannot use infinity as a point of reference. For a point charge, I could use this as a point of reference, infinity as a point of reference, but for a line charge which is infinite, I cannot use that one. The reason why this happens is because the electric field of a point charge goes as 1 by r square, it decays as 1 by r square, okay, and an integral of 1 by r square will give you a finite value at infinity, whereas the field of a line charge and the field of a sheet charge or a plane charge, we are going to talk about that in the next class, will go as 1 by r or constant. Therefore, at infinity you cannot use them, because at infinity the charge, the integral values, sorry, the values of these expressions are not going to be 0. The primary culprit being the slow variation of the electric field. Okay. These conditions will become later very important when we talk about radiation. Okay. Until that point, let us not worry about it. But what we have to do meanwhile, if you want to solve this problem of putting a reference, is to pick any other point apart from infinity as my reference, and then start finding the potentials from that point. Okay. So, this is not the infinity as the reference point, but any other point or any other point in the at any other point has the reference, and all the potentials will be calibrated with respect to that point. In fact, this is practically what happens. You take a coaxial cable, we are going to discuss that shortly. You take a coaxial cable, it will have an inner and an outer conductor, okay, which one can approximate as one line and another line. Okay. Outer line is where we connect a voltage supply, I mean connect a ground, and then we say that that is the point of 0 potential. Okay. And the inner line will be charged, and there will be an electric field between the two. We are going to calculate that one. This is an example of long line charges and our inability to use infinity as the point of reference. Okay. So, you can of course object to this entire thing, saying that in practice how am I going to realize an infinite line charge, and you will be right. This problem of idealization has happened only because we considered an infinite line charge. In fact, here is a nice puzzle. What is the total charge contained by the infinite line charge if the line charge density is uniform? If you now go from minus infinity to plus infinity rho l dz, what will be the value of the total charge in this contained in the linear charge density? You try to think about a little bit on this total charge. Okay.